Hello there. This week we're going to go on to maxima and minima problems. So although you already should know that and you should really be working through it, I thought what I'd do is publish a few really short videos just to show you how actually to do this and talking your way through the actual sheet. So what I've done is that started off here with a simple maxima and minima problems section. So I've put in a few things for you that might help you a little bit. So the first example would be supposing that I have an example of, say, a solar-powered car. Right, that would be a good example. As you can see there, we've got the solar-powered car. So the solar-powered car, the idea is that solar power comes in, and the car has to have the maximum range on that charge that it's got from the solar power. So how do you actually do that? So that's a maximization problem. Or you may have an example here of, if I can just show you, there we go, so I'm having a wee bit of trouble here. Here we are. Or you may have an example in business where you've got a new product out and you want to maximize the profit. So how do you do that? For example, do you increase the price, in which case you would get more unit profit, or do you decrease the price? Because if you decrease the price, you get more sales. And so which one do you do? Or do you do a mix of both? So how do you maximize your profit? Another one you could think of is a range of a projectile. So what angle do I throw a javelin at, for example, to maximize its range? Now in dynamics you find out that's 45 degrees, but how do you actually prove that? And then one that I had to work on at Glasgow, which is a moon rocket. So our team had to work out how do you get a payload, a rocket in this case, a spacecraft to the moon for minimum fuel. And that turned out to be a really difficult problem. So all of these involves finding the best way to do something. The technical word for that is optimization. You're trying to find that the largest or the smallest you can make something. So the big picture we're going to look at is that if you consider this example, we've got a function here, and that's a high point, and we call that a maximum, and that's a high point, and we call that a maximum as well. These are low points, they're called minimum or minima. Now that one is the biggest maximum, so we call that a global. This one is only a maximum in this area, but it's not a maximum compared to that, so it's just called a local maximum. This one is a local minimum, and this one here is a global minimum. Now, how do we find these things? They're very important. So what I've drawn here is the tangent lines. So if I have a look at the green tangent line, then just before it, we've got a positive gradient that's sloping up, and then it reaches the maximum, and then it slopes back down again. And then if we look at the minimum, so it's sloping down, same as this one, and then when it's past the minimum, it slopes up. And again, we've got a slope up, and then past the minimum, it slopes down. So we've got positive and negative gradients. However, the key point is this. This is the key point to the whole video. At the maxima or the minima, the tangents are horizontal. So the global maximum, the local maximum, the local minimum, and the global minimum, the tangent is horizontal, which means the gradient is 0. dy by dx or f dash x is 0. So that's really what we're looking for. To locate these, we're looking for the points where the gradient is 0, dy by dx is 0. Now there's one little problem. We've got this guy here, this cheeky guy here. Now that's neither a max or a min, and yet its gradient is 0 at that point, and that's called a point of inflection. We're not really going to bother about that guy too much, just be aware that it does exist. So here's what we're going to be doing. To find the stationary points on a graph, you're just going to simply differentiate the function, and you're going to set it equal to 0. So if the derivative is equal to 0, that gives you either a max, a min, or a point of inflection. Now we call these things turning points or stationary points. So it locates the stationary point. It actually locates the x value of the stationary point. And then to find out if it's max or a min, we call that the nature. You form the second derivative, which you're already familiar with, f double dashed x. And we're going to use this rather strange rule, which is if the second derivative is positive, then strangely it's a minimum. Or if the second derivative is negative, then strangely it's a maximum. What's the opposite of what you would actually expect? Seems weird, but it's true. So we're going to apply that to all the problems that I'm going to talk about. So hopefully that helped, and that's just a little introduction, and I'll come back with some problems pretty soon. Thank you very much.